Alright, so today we're going to be talking about limits, right? What is a limit? Well, basically, a limit, a pretty crude definition is, it's just the value, let's call it the value L, a function tends to at point C. If you want to be very mathematically rigorous about it, the definition is the function L, or the function f, rather. The function f has a limit L as x approaches some real number c if given any positive, another positive number, positive epsilon here. There is a positive delta such that for all x, right? So this is just for all x. 0 is less than absolute value of x minus c. It's less than delta, implies that f of x minus L is less than epsilon. Now, this is called the epsilon delta definition, and it's pretty confusing, if I had to say. So, one sort of explanation of this is, let's say we have this function over here, right? I'm just drawing a graph, and then this is at point C, right? It takes on this value L. And then we have C plus delta, and then C minus delta. Delta is like an arbitrary integer, then L minus epsilon, L plus epsilon. Basically what we're saying is, this function f, has a limit L, right? As x approaches C, right? X is approaching C, has this limit L. If we have any given epsilon, there's some sort of delta. Basically, we can form an interval around C in a way that it also graphs out in the function itself, right? If this is not very clear, I wouldn't really stress about it too much, because in practice, finding limits is very simple, and we'll get to that. So let's exactly do that. Let's get to actually finding limits, right? In terms of this, just keep the first definition in mind, where basically a limit is the value L a function tends to at a point C. Alright. So, before we get into some examples, I just want to make it clear. Note, the limit of a function does not depend on the value of the function at the point. So what am I saying here? Well, basically I'm saying that the limit of the function, the value of the function at the point, are independent. The function could not be defined at the point, and it still has a limit, or the function, the value of the function at the point is something else, and the limit is something else. This will be more clear with examples. So let's just have this classic example. Let's have this line, right? We'll call this f of x is equal to x squared minus 1 over x minus 1. Now, clearly this is the same as x minus 1 times x plus 1 over x minus 1, right? So these two cancel, you get x plus 1, right? But it's not defined at 1, right? Because the original function has x minus 1 in the denominator, so it's not, that open circle means it's not defined there. And then this will be 2. So, final limit of f of x as x tends to 1. Now, we sort of see, through our epsilon delta thing, that at point 1, the function approaches the value 2. So, intuitively, it should be equal to 2. And see how at point 1, the function is not defined yet, instead of a limit that's defined there. Now, let's sort of add on to this, right? Let's instead make this a piecewise function, right? So, f of x is equal to x squared minus 1 over x minus 1 for all x not equal to 1, and at x equals 1, we have, it's just 1, right? So, our new graph will sort of look like this. What's the limit? So what, the limit here is still 2. Like, although the function is defined at 1 and the value is 1, the overall graph of the function tends towards 2, so the limit's 2. Another way to sort of reason about this is, if you go back to sort of epsilon delta definitions, we form a sort of interval around here, around these 2 points, right? It's forming an interval around this sort of curve, right? And that sort of hints at the limit being 2. It's not forming an interval around 0.1. So, we sort of have our basic intuition about limits. Let's just talk about the properties of a limit. And I'll just list them out because, to be honest, they're pretty simple, they're pretty intuitive. So property 1, or before, let me just define the limit as x tends to c of f of x is equal to L, and then let's say the limit as x tends to c of g of x is equal to c, or sorry, m. Alright. There. So given these, we have the sum rule, the product rule, the difference rule, constant, quotient, and finally power. Basically, what the sum rule says is the limit as x tends to c of f of x plus g of x is simply L plus M. Similarly, for the product rule, limit as x tends to c of f of x times g of x is Lm. We can guess how the difference rule will look like. Pretty simple. Constant just means limit as x tends to c of some constant k times f of x. Also this f of x is chosen without loss of generality. It could be g of x, but just kl. Limit as x tends to c of f of x over g of x is simply L over M, and this is with the caveat of M is not equal to 0, and then limit as x tends to c of f of x to some power, like, I don't know, n is simply L to the power of n. With these rules, we kind of see how it's pretty intuitive how we manipulate these, and whenever you have problems with limits, you can combine multiple of these properties to get to your final answer of the limit. Let's just do a quick example on the property of a limit. So find the limit of as x tends to c of x to the power 4 plus x squared minus 1 over x squared plus 5. Now there's two ways to go about this. I mean, you could treat this whole sort of term as one function, or you could treat the numerator and denominator as separate functions, and either one is a logical approach, right? So, I mean, for this, we just plug in c, and then we get our answer, right? So, c to the power 4 plus c squared minus 1 over c squared plus 5. If this doesn't really make sense, you could try to talk about how you put the limit in each one of these terms, right? And then we add it up. So, like, this is the same as limit as x tends to c of x to the power 4 plus limit as x tends to c of x squared plus limit as x tends to c of negative 1 divided by the limit as x tends to c of x squared plus the limit. Now we clearly see like the limit as x tends to c of like x is just c, and then when it's at the fourth power we use the power rule, and then that's how we got like c to the power 4, and then similarly the case for x squared. The limit as x tends to c of like a constant is just a constant, so it's just negative 1, and then the values of the denominator follow like that as well. Alright, so let's look at an interesting example. Find the limit as x tends to 0 of sine x over x. Now, later on we'll see how we can do this pretty quickly using L'Hopital, but right now we don't know what L'Hopital's rule is. So how do we do this? Our traditional method of plugging in the value is not going to work because the limit's not defined. Sine x over x is not defined at 0, right? So if you try plugging in, we're going to get like sine 0 over 0. And now, I mean, clearly this is a problem, right? So whenever you have this right now, you try solving this graphically. So we graph out sine x over x. If we do that, we see that it sort of looks like this. It's a damped function, right? The value at 0 tends to 1. It's not defined, but it tends to 1. And, I mean, going back to our very first example, this just means that the limit is 1. The limit's 1. Alright. Now, are there cases where the limit's non-existent? And the answer to that is yes. So, let me work over here. Limit as x tends to 2, x cubed minus 1 over x minus 2. So, I mean, first we could try factoring out x cubed minus 1 to see if, we can remove that denominator, because x minus 2 at x equals 2 will be 0, right? So that's a problem. But we see that this will not really get us anywhere, right? This is the factorized form, and we still arrive at a problem. And so, like with the previous example, we graph this out. When we graph this out, we see that the function sort of looks like this. Also, I mean, as you get more and more into calculus, you'll see how to graph these functions fairly quickly. right? And this is at point 2. Now, we see here that as we approach 2, there's really not one point that we're converging on. And because of that, the limit does not exist. Or DNE for short. Now, I mean, the last example might have been a bit crude, right? So how do we formalize, or how do we know for sure that a limit does not exist? Before that, let me define something called one and two-sided limits. Basically, a right-hand limit which is denoted as limit as x tends to some c from the positive side. So you're coming from, right to left, so it's the right-hand limit of f of x. And then so the left-hand limit is denoted as limit as x tends to c from the negative side, so you're coming from left to right, so it's the left-hand limit. So these two are known as the one-sided limits, and that basically tells you like what the value of the function is approaching when you're coming to point C from the right hand, from the left hand. And basically, we're told that whenever these two one-sided limits are the same, so the limit as x tends to c from the right side is equal to the limit as x tends to c from the left side, we have, which is equal to some L, that means the limit as x tends to c exists, and that's equal to L. Whenever limit as x tends to c from f of x is not equal to x tends to c from the left side, that means the limit as x tends to c does not exist. And we can connect that to the previous example where we saw the limit as x tended to c from the right side was going towards positive infinity, where from the left is going towards negative infinity, and clearly that doesn't really match up, right? So the limit just did not exist. Let's go over some more examples to sort of strengthen this thinking. Suppose we have a piecewise function, right? It's not defined here. Okay, this is 1, this is 2. And then similarly, this is 1, and this is 2. So we're told to find the limit, and then this is some function f, right? The limit of f of x as x tends to 1. Now, the limit of f of x as x tends to 1 from the positives, the right-hand limit of this is 1, right? Because when we're approaching from the right hand, this is around 1. And we know that the limit of f of x as x tends to 1 from the left-hand side is 0, right? Because we're going here, and this function approaches 0, even though it's not defined there. I mean, even though it's not defined at 1, it approaches 0 at 1. And clearly these two are not equal, right? So, what did we say last time? When the two one-sided limits are not equal, the limit does not exist. What about the limit of f of x as x tends to 2? If we do a similar analysis, the limit of f of x as x tends to 2 from the right side, we get that's equal to 1. And then the limit of f of x as x tends to 2 from the left side is also equal to 1, right? Because this is from the right side, and then this is from the left side, both equal 1. That means because the two one-sided limits are the same, our limit is 1. And it's defined. Note that at point 2, the function's value is actually 2. The limit of a function does not depend on the value of the function at that point. And this goes back to our epsilon delta definitions, where when we form that little interval around 2, right, this little delta, and this minus delta, and this little, some sort of epsilon, and then some minus epsilon and epsilon, right? It forms the interval around this point, not here. So our limit will be 1. Alright. Now, finally, we go to the sandwich theorem. And this can help solve some limit problems that are a bit tricky and interesting. Before you learn L'Hopital's rule. So basically the sandwich theorem states that if you have some function g of x, which is less than or equal to some function f of x, which is less than or equal to some function h of x, for all x not equal to c in some inter around c, then the limit as x tends to c of g of x is equal to the limit, and the limit of x tends to c. So basically, if we have a function g of x, which is less than or equal to f of x, less than or equal to h of x, for all x not equal to c around some interval c, and the limit as x tends to c of g of x is equal to the limit as x tends to c of h of x, then we have the limit as x tends to c of f of x is also, and these two values are equal to L, then the limit of f of x as x tends to c is also L. So, what is this exactly? Let's look at an example. Find the limit as x tends to 0 of x squared times sine 1 over x. Now, here we have two functions. We have x squared and sine 1 over x, right? That are sort of combined in here. We sort of can try to find another two functions that sort of bound this function x squared sine 1 over x. Let's try negative x squared and x squared. We know that negative x squared is less than or equal to x squared sine 1 over x. And why is that? Well, we know that the sine of any value takes values between -1, right, and 1. So we know that the sort of least value that we can have of sine 1 over x is -1. So it will always be greater than or equal to negative x squared. And then the most value we can have is 1, right? So it will always be less than x squared. And in fact, we have found these two bounds of these two functions. And we know that the limit as x tends to 0 of x squared is equal to 0. And similarly, the limit as x tends to 0 of minus x squared is also equal to 0. So we found something very interesting, right? By our last, from our statement for theorem, this is g of x, right? It's our lower bound. this is f of x, right? What we're interested in finding the limit of, and then this is h of x, right? Our upper one. And we've found a way to bound f of x around these two functions around some interval around 0, right? And we know that the limit of these two bounded functions, or like the ones that we're bounding by, are 0. And that means by the Standards Theorem, the limit of this is also equal to 0. And we can verify this by graphing these two, right? So when we graph it, we'll sort of, okay, now we graph. We have this as x squared, and then we have this as minus x squared. And the function that I gave is sort of like this. Yeah, it's pretty crazy. Ugh. This is a terrible drawing, but yeah. And basically at point 0, all of their limits are 0. And that's pretty cool. The Standards Theorem is pretty powerful. Alright, so that's basically it for limits.